DP. Okay, it means double of inverting stage. And now N represent here total number of odd stage, odd number of inverter we have put in the series. Okay. Look at this waveform. Okay. This is the one of the very simple diagram for ring oscillator. Here what I put, three odd inverter stage connected in series and feedback. One feedback path applied. Feedback means a sample of output signal or output component applied to the input. So practically you can see in the circuit, there is no input applied. Do not have any input. So it can generate oscillation at the output Q based on this output signal instead. Okay. This is the today's in the project 2, which I want to highlight how to generate frequency based on this CMOS inverting stage. Okay. Software everybody comfortable? So all this frequency is always based on this formula. F equal to 1 upon twice of n into tau of p. Because you know frequency is opposite of the time period, where time period is a lower path, higher path. That going to make twice of p and inverter stage. Or propagation delay of the discharging and charging path, number of inverting stage. Now, first of all, let's assume, first of all, I'm assuming that initial output was 0 into this electronic circuit. Initial output 0, the same output going to connect over here. Now, due to the inverter NOT gate, it will be inverted to 1. This 1 again inverted to 0. This 0 again inverted to 1. So this value will change to 1. Now this 1 going to apply over this input. This become 1. This will give the output 0. This and third inverter give the 1. This again will go back to 0. So third output will come here 0. Again 0 will go to the input. So 0 will come input. Here become 1. Here it becomes 0. Here again it will become here 1. So this is going to make an infinite loop between 0, 1, 0, 1. Okay, so this is going to make infinite loop because of the odd number of inverting stage. So now this 0, 1 output, if I'm going to display on the CRO or the logic analyzer, I will get this type of waveform, 0. So now to change the output from 0 to 1, it will take some time. Okay. Now how much time it will take depending on the delay of this inverter. Total delay of the inverter. So it will remain 0. After some time, it will become 1. Okay. So again, it becomes 0. Again, it becomes 1. Again becomes 0. Again becomes 1. So now this is going to display this type of waveform, which is nothing but oscillatory waveform. Okay. So in this way, we are able to generate oscillatory waveform between the 0, 1, where 0 is the lower voltage, 1 is the high voltage. Okay, so this is about how the output should appear. Okay. Now here we will focus on how to map the generated frequency, and we will put you people to work on the same design and oscillator and try to measure the frequency of your designed oscillator and create a report as the project 2, as you did yesterday. Okay. Let me go proceed for next. Okay, so here I have shown one of the diagram which I have used according to my CMOS network. Okay, in the CMOS network, what I shown here first, I have shown PMOS, NMOS. That is my first NOT gate, second NOT gate, third NOT gate. PMOS, NMOS connected in series. It and output are connected back at the input. That is going to make map the oscillator. Simply, I replace one NOT gate by the CMOS inverter. Now, when I'm going to work on it after simulation, I will get this type of oscillatory waveform. Okay, this type of oscillatory waveform should appear. Okay. Since I took here three inverter stage, I will have some frequency. If I take five inverting stage, 11 inverting stage, or 21 inverting stage, number of inverting stage going to increase, frequency will be different. Okay, so here I will suggest everyone to try to take some different number of inverter stage, different number of inverter, but only odd number, and try to measure how much frequency you are going to obtain. Okay, uh, but up to here comfortable? Fine. So now let me proceed next. So now here in this case, you will found one challenge. Here I have assumed initial value of output is 0. Okay, we can assume initial value 0 because we are assuming by mathematics. Initial value 0. But how can we tell electronic circuit practically to make to assume initial value? So in the electronic circuit, we don't have option to assume. We have to provide initial value. So in order to provide initial value, we need to do some change into the circuit. Okay, let me go for next slide now. Here, let's see what I'm going to do now. Here, I have shown you five-stage ring oscillator. So here I have put one NAND gate in the front and four NOT gate. So since NAND gate, one input equal to one, and we know in given as enable. So when enable going to connect to the first NAND and the one feedback path. Now I'm claiming that it is also an oscillator. Okay, now in the NAND gate equation, we know it is the A dot B whole bar. So if one of the input equal to one, this will be equivalent to NOT gates. In the NAND gate, if one equal to always one input, this will be NOT gate itself. So when I say enable equal to one, so it will become a NOT gate and it will act as odd number of NOT gate with feedback. So it's the oscillating. But when enable equal to zero, so this output going to become always one. Okay, so this is not going to act as inverter, so it will not able to generate frequency. Okay, so here our experiment. So this is my complete transistor level circuit. Here, first NAND gate, I have taken two NMOS in series, two PMOS in parallel. Now, four CMOS inverter, which is made by the PMOS NMOS. One feedback path diagram is same. Now here, you will surprised to see that when enable equal to 1, it will generate a frequency. But when enable equal to 0, it will not able to generate frequency. Okay, so that is our experimentation, which I want to do here. How to generate frequency with the help of enable. Okay, so here we don't have way to providing assumption of initial value, but we are enabling the circuit itself. So one NAND gate and then followed by the inverter stage. So total we have odd number of stages. Okay, guys. So now here to experiment this type of circuit, we should have some EDA tool like in the previous discussion. I have shared one of the tool which is known as DSCH. You must have remember for that DSCH software where we are working with transistor level. So here I'm going to use for this project too. I'm stretching this part into the DSCH tool. Okay, this is my uh, workspace where I have shown this black background, or if I wish, I can take the white background. Okay. That is my workspace. And this is a my library component, where in the bottom I have shown you PMOS and MOS. Okay. So just the circuit diagram which I have shown on the last slide, try to implement via this software. Okay. So first of all, the first part was the NAND. So I'm going to take one PMOS, two and a PMOS in series, and two NMOS in NMOS series, PMOS parallel. So I am going to take components. Now here I have shown you the mirror. Okay, I'm showing you the mirror of this PMOS so that it can be, and I'm mirroring this PMOS NMOS also. Okay, so that our wiring will be simple. Okay, so I'm going to connect like it. Now here is the wiring option to us. Okay. Now here again I have connected with wires. Now here one input which I have mapped like it, and second input which I have connected like it. This I made as a NAND. First option. Provide here power supply and ground. So that is the required part. Ground input. Provide here the power supply. Now this is I'm going to provide a button, which button will act as enable. Okay. So I'm going to provide the name. Uh, so here I'm going to provide the name enable. This is my NAND. First part I have made. Now what I discuss here, we should have odd number of stage. So I am going to take NOT gate. That is a one PMOS, and I'm going to put one NMOS. That is my first inverter. Here I'm going to directly connect it. Okay. That is my first inverter. Okay, now I'm going to take copy. This is my copy part, so I can use this shortcut. I'm going to draw this one box, so this complete will be copied. Okay, I have put here. I think it's extra wire. Yes, here we have got extra wires. Okay, so here I'm going to take copy again. So replicate it. So both four will be copied together, and it is going to make four NOT gates. So let's see how easily I have made it. Okay, how easily I have made it, four NOT gate and one invert. Okay. Afterwards, what I'm going to do, simply I have to make the complete the circuit. So I'm going to connect all the four input together. And here I'm going to connect all ground together. Okay. Now I'm going to take the ground from the search library and map over here. And take one VDD and mapping over upper wire. So power line has been made. Okay, guys. The next stage, I'm going to take this wiring, this wiring to connect output of NAND gate for the input over here. So this output connected to this NOT gate. So total, I have got 5 components. So here, this output of NOT gate is the input for following NOT gate. Output for each NOT are connected back to back. Okay. So here I have made total 5 inverting stage in series. Okay. This is my 5 inverting input in the series. So here, what is the next last option? Last is that we have to provide feedback path. Okay, we need to provide feedback. Feedback is we will take one output signal. Let me delete this part because I unnecessarily it came out. Okay. What I'm going to do the next one is I have to take the one feedback. So I will take in the NAND gate one input given enable, second input is over here. So I'm going to provide the second input like it, and this is going to connect as the feedback. Okay. So from here I'm going to take second input to provide the feedback for output stage. Okay. That is my complete network, complete circuit for ring oscillate. So here I what how I made it. First stage to provide NAND, following by four NOT gate together. That will make a ring oscillation. Very simple network. Afterwards, at the network we are going to put one light so that it can we have to observe the output. So that I'm going to put one marker that is a light. So I'm going to give the name clock out. The color you can change according to your required. Right. So now when I'm going to simulate this part, okay, when I'm going to simulate this part, here you can have this type of combination. So what are the output I am getting? First of all, here output is constant because there is no enable. But when I'm going to provide enable, you can say we have this type of on-off combination. Okay. So I can show you here pin state. It will display what are the values. So I'm going to make it slow, simulation speed slow, so that I can have this type of connection. So as I have displayed during the discussion, so how the 0 1 0 will 0 1 0 1 will appear after some delay. That going to provide a oscillation. Okay. So now I'm going to stop the simulation and you can visualize in the waveform. You will have this type of output waveform. I'm going to zoom it. If I'm going to zoom it, see here, when enable was 0, there was no oscillation, output is constant. But when I'm going to provide enable, it will start generation of the frequency. It's going to generate oscillation frequency. Now here you can measure is what are the, okay, here you can do the measurement, what are the frequency, what is the frequency of this waveform. I would like to simulate it again. First of all, let's see, I'm going to make it 1. Stop it. Now, look at the waveform. So, sorry, I have not made enabled. Let me take one waveform first. Here I have got this type of waveform. Enable 0, no waveform. Enable 1 is the waveform. Now, how to measure frequency of it? That is my interest. Okay. The frequency which I am going to showcase here, look at this frequency. So this is a my one time period. That is a my 1 0. There is a 1 1. What is the time of it? So here I can measure 28 to 29. Here we have total 10 divisions. So I can make, so here you can take the one rough scale to 28.32. Here 30. Here we have the one complete period 31.1. 28.3 to 31.1. So how much the total delay? So around 1.8. 1.8 nanosecond. Okay. So 1.8 nanosecond is the total one time period. So frequency will be 1 upon time period. So you can measure total frequency will come around So 1 divided by 1.8, it will come around 0.833 gigahertz. Okay. So okay, so what I'm going to discuss here, because of this oscillation, the total time period which I have measured t equals 0.83 nanosecond. So what is the frequency? So frequency, I am going to write frequency equal to 1 upon T. I have got 0.833 gigahertz. That is the unit of frequency, and this value is equal to 833 megahertz. Okay, it is going to equal to frequency equal to 833 megahertz. Okay, so this is a very simple circuit for ring oscillator through which we are able to generate frequency of 833 megahertz. That's a very high frequency. Generally, in our computer system, we are using 3 gigahertz of the i3 processor, generally around 3 gigahertz of the frequency. So we can generate this amount of the frequency. Okay. So now, what is the expectation from you that try to do learn this ring oscillator circuit and try to generate different range of frequency. Here I have did experiment with only five inverter. Try to make different type of inverter, like try to do seven stage, 11 stage, 19 stage. Try to make some different number of the inverting stage, which first circuit will be NAND, so that you can enable. Okay. So try to generate a different range of frequency via this configuration and try to obtain a report on your learning for this oscillator. Okay. So here I have used this software already. I have shared this tool with you, but I'm not limiting you. Whatever the tool available to you, like multi-sim, or you can go MG5, or you can go for the Proteus. Which tool is available with you? You are free to use any type of tool. Okay, and try to do this some work on this. So better guys, I hope so you got some idea about it, how to work with what we want to discuss about this one. What was the ring oscillator? What are the importance of ring oscillator? And how it is an integral part of the PLL of the circuit. The PLL is a very one of the benchmark circuit of the VLSI designer to generate high noise. Okay, now in this case, here I want to look at attention that setting of certain value. If you do have option in your tools, just try to learn that, like in the CMOS inverter, it always suggested that PMOS must be 2.5 times wider than NMOS. Then only we will get complete inverting stage. Okay. So here what I'm going to make, since I have taken 120 nanometer technology, W I have fixed here 1, W I have fixed here 2. Okay. So now here have the option, I can select foundry. Here I took the text file, that is my CMOS 60, 80, 120, 180, 250. So if I'm going to take some lower stage, so you can have this deviation, how our transistor will change, but I need to redesign the circuit. So see that part. Suppose in this case, if I'm going to change the W value, if I'm going to make W equal to 3. Now you can visualize how the waveform will be affected. LW of NMOS, I put the same. But W of PMOS I'm going to change. Now see how it will affect the waveform and what are the range of frequency. Similarly for NAND, fine. So now I'm going to run this one. So initially I will get similar type of expectation. I will get waveform. Now pause this work. Now I will have this wave. Look at this waveform. So now with this, try to measure the frequency of it. So here I will what I have given that this is my complete one time period. Shall I zoom out it? Yes. This if I get a complete one time period from this time to this time. So now here try to measure what are the value. Okay. What are the value of this my complete waveform? So here if I take, let me take some better value, like suppose it was starting from 181 and going to end with around 86, so total we have 10 division. Division is zero point 0.5 nanosecond per division. So zero point 0.5 is a division for it. So how much division I'm going to take? So 1, 2, 3, 4, 5. 186 point, mm, 0.5 into 5. 2.5. So 188.5. So 181 minus 188.5. Around 7.5 nanosecond. If my propagation total delay becomes here 7.5. So you can measure the frequency, what 7.5. It is going to make 0.133 gigahertz. It means around 133 gigahertz. So what our discussion here? So for our discussion is the oscillation frequency. It depends on delay of each inverter and number of inverting stage. Delay of this NAND, delay of the NOT, if I assume equal delay, the delay of the stage, inverting stage, and number of stage, where delay is proportional to the size of transistor, the width of the PMOS as well as NMOS. Okay. So that is my uh, one of the project today, that is how to design oscillators, ring oscillator based on the at the transistor level. Since we have started, we have learned both the parts in the transistor level as well as digital components. Apart from it, here we have option. We can make Verilog programming also. In the Verilog also, we do have option. We can make uh, ring oscillator into the Verilog coding. In the Verilog, what we have to do? We have to simply do gate level modeling. Take one NAND gate, take the 4 NOT gate in series, and try to do one feedback. But remember that in the feedback, here this output are providing as the input. So we have to make this as in output, because this is going to act as output as well as input. So this port should be in out. It can work as a in the Verilog coding also. Or this is the one of the modeling style which I have displayed as the switch level modeling of Verilog coding. So with the switch level modeling, we are using NMOS, PMOS switch to design the circuit. Okay. Simply, we are going to use a similar to gate level modeling. We are calling one gate from the library. Followed is the port mapping should be output than input. Similarly, here we are calling PMOS, NMOS from library, and there are certain inbuilt delays. That's hash 8, hash 2, hash 6. There are some inbuilt delay. Because of this delay only, we are able to generate frequency. So call the NMOS PMOS from library and provide the output, input, and enable is my control. Here three input to the one transistor. That is my drain. Here we have source, and here is the my clock is the gate terminal. Okay, that we can change this value. If I'm going to change 3 by 0.2, 0.1, delay will be different. So delay depends on the width of the transistor. Okay. So here, this I have shown this is a complete picture as a the model of this transistors, how to generate model file, and finally we can make this type of learning in the either Verilog coding or we can go for transistor level design. Okay. So here it is a intent of discussion for today, where I was focused on the learning behind CMOS ring oscillator. Fine. So now here I am repeating it again. So you need to create a report on this topic, that is my ring oscillator, but try to choose the number of odd number of inverting stage according to your choice. Keep first as a NAND, or you can try with NOR also. That will also work on the similar type of a similarly. Because NOR is also nothing but A plus B. So if I'm going to put input 1 or input 0, so we can have the enabling feature. Okay. So here option is take the first input as an AND or take the inverting state. And you try to experiment with different number of odd numbers, and try to see for which odd number if you have the frequency criteria. Now try to mention that for higher, if I take lower number of stage, what was the frequency? Odd number of more number of stage, what is the frequency? And learn in try to learn like it. Uh, if the number of stage are going to increase, what are the impact of this? Okay. In the formula which I have mentioned in my slide, that is the formula I have mentioned, F equal to 1 upon N. So it means frequency is inversely related to N. It means N going to increase, frequency will decrease. But try to prove it by means of your circuit diagram. You could experiment with some four or five circuit you can try with different dates and try to make one tabular or one waveform how the frequency related with number of odd. Okay, guys. Okay, this was the one project topic two which I have brought for you today. So now I'm open to you. So if you have any question or any discussion on that, we'll continue.
इतना जल्दी हम्म खत्म
It's on query the due date. The date of submission, I just gave some message in the admin from your group. Better the admin can tell you about it, what, how to submit and when you have to submit for it. Okay, guys. So now I think no more query from now. So this was the complete session which I brought for you. We need to submit, subtract that learn yesterday. Yes, yes, very good. Because we have the two projects for this your learning today, learning year. We have to make two different reports. One report for your adder cum subtractor, and second report on the today, that is the ring oscillator. And try to put up the content, whatever we have report, like how I think format. I think host is there. Actually, I'm not. I think Redmi Lohit sir can tell you better how to what are the format for report. Okay. So now any I can give you the format like first of all in the simple way. Create one your title, then your introductory part, introductions. Now keep the one complete block diagram or circuit diagram. Write certain theory part of it, like the Boolean equation or truth table, or you have the certain formula to analyze, write the circuit diagram of it. After that, the screenshot of your software, like the program you have used, like in the Verilog coding or the circuit diagram, translatable diagram. Take the screenshot of the code or screenshot of the circuit diagram, simulation waveform, and what analysis of the simulation result, like what are the input you have applied, how the output are responding in the waveform, whether your program is correct or not, what is expected output, and what you have got the output. After that, you need to discuss each part and conclusion. What we have complete conclusion for this your report. You can make a report of 5 to 6 page for one project, that is sufficient, and add certain reference at the end, at least 4 to 5 reference. This is general format for any type of report usually we